Hello and welcome to part 2 of lesson number 4 in Unit 7 Exponential Functions in our grade 11 University College math class. First half of this lesson, or the first part of this lesson, was us creating some tables of values and then graphing the resulting tables to get a look at 3 different types of exponential functions and just to sort of check out some of their characteristics, especially as they pertain to some of the concepts we've been tackling all semester long, things like domain, range, and then specific to this unit, looking at things like growth and decay and introducing the concept of an asymptote, a value that a function approaches but will never actually touch. Second part of this lesson is going to be us making a comparison, as I said before, between the types of functions we've encountered in the past. Linear from grade 9, quadratic from grade 10, and now exponential functions in grade 11. So let's jump in. Visually, from an equation, how can you tell whether something is linear, quadratic, or exponential? So let's have a look at f of x equals 2x plus 3. So this is going to be, let me just check my coloring here. This is going to be linear. The reason that this is going to, or the reason that I can recognize this as being linear is because it's a first degree function, which means that I'll write this underneath, first degree, so the largest exponent on a variable is 1. Now, some students will mistakenly say like, oh, there is no exponent here on the x. There is an exponent, we just don't bother to write it, but there is an exponent of 1 on that x even if we don't write it. So it's not that there's no exponent, it's just that there is an exponent that often we don't choose to write, and it is 1. So any first degree function, i.e. a function that has as the largest exponent on any variable 1, that will be linear. Let's look at our second one, g at x. So g at x equals x squared minus 2. So this one is going to be quadratic. And I know that because the largest exponent on any of the variables is 2. So we call this second degree. It's a second degree function. And I'm going to just shortcut it because I don't want to spend all of my time just writing, but exponent, the largest exponent that you will see on any of the variables will be 2. So there it is, just hanging out there above the x. There's our squared. So that's going to be quadratic. Finally, if you have h at x, how do we recognize what type of function this is? Again, I think you're noticing now that the key is to be looking at the variables and see what's happening with them. In this case, the variable is actually the exponent. So this one is going to be exponential. And as we know from working through this unit already, exponential functions have as variable, the variable is the exponent. Okay, and that is visually how you can tell apart, just given an equation, what type of function you're dealing with. Linear is a first degree, which means the largest exponent on any of the variables is 1. Quadratic is when it's a second degree function, which means that the largest exponent on any of the variables is 2. And finally, it's exponential if the variable is the exponent. So there is from the equations. Now tables of values represents a challenge for me because I don't want to force you to do all these calculations as I would do in class. So what I'm going to encourage you to do here is, again, hit pause and then copy these tables out. So these tables represent sort of a completed table of values for a particular function. So here's f at x, 2x plus 3. This is the same example we did above. But when we input these, oops, I want a highlighter. When we input these 7 values, these are the 7 outputs. So again, if you can imagine, 2 times negative 3 is negative 6, plus 3 is negative 3. So that's how we're populating the table. And then first differences, of course, are negative 1 minus 3, which is negative 1 plus 3, which gives us 2, etc. So I'm going to zoom out. What I'd like you to do here is hit pause, create these tables in your own notes or on a piece of paper, and then I'm going to come back and talk to you about them. So do that now. Okay, you're back. Let's have a look at the first one. So once we complete our table of values, the first thing we do, and this is sort of a series of tests that you perform on the table of values, And this, of course, assumes that you can't see the equation, because obviously if you can look at the equation, then you can determine it by the equation. But I'm saying, imagine I just gave you a table of values, and you didn't know what had generated it. The first thing you do is you do first differences to check that it's linear. If the first differences come out common, so if first differences, and again, first differences has a clue right in it. First differences, of course, are subtraction. So when I talk about first differences, it's the first set of subtractions that you do with the output values, the y components of your table. So if first differences are constant, we know, therefore, this is going to be linear. That is a pull from all the way back in grade 9, so that should be very familiar to you. If we look at our second table of values, again, same idea here. We've generated this based on input values. I've given you an equation, but pretend that I haven't, so let's just scooch that up. So this is the table I give you. How can you determine what type of function this is? Well, the first thing you would do, the first test always, is to do those first differences. So you do first differences. They're not constant. So here we go to second differences, and I want you to remember that second differences are same as first differences, except you're basing it on first differences as opposed to the original y values. So -3 minus -2 is -3 plus 2, or sorry, -3 minus -5 is -3 plus 5, which is 2. And that works its way all through the table when you do that math. So if our second differences, and again, when I use the word differences, we're talking about subtraction. If second differences are constant, therefore this is going to be quadratic. And again, that's a pull from grade 10. We know that, or should know that. When our second differences come out constant, it's going to be quadratic. The third and final one, this is a bit beefier of a table here. What I did was just to sort of illustrate the sort of nature of how this works out. When you have functions like this, we're going to get a chance to see that same patterning as when we did the when we were graphing the functions above that were exponential. What you're seeing is this patterning where you've got 2 1/2, 4 1/4, 8 1/8, etc. But what you're going to notice as we head into this, so again, I'm giving you a table of values. You're going to try to figure out what it is. First thing you're going to do is work the first differences. They're not constant. Then you'll try the second differences, not constant. Now in theory, you could continue to try more differences. You could do third differences or fourth differences to see if it's a cubic or quartic function. Again, for us, it's not that that's not the right approach, it's that that just isn't a type of function that we have explored yet this year. So our recommended third test is then to sort of switch away from differences, which are subtraction, and head towards ratios. And remember that ratios are division. So if we were trying to figure this value out, it would be 1/4 divided by 1/8. So again, I'm using these first two values right here. One lower value in the table divided by the value higher in the table. And some of you might be confused because I've kept them as fractions as opposed to decimals. But that would be 1/4 multiplied by the inverse of the second fraction, which gives you 8/4, which gives you 2. So that's sort of how I do those calculations. And I would just do that calculation all the way down through the table. And what you find is that and it's important to say y ratios as opposed to just ratios. It refers to the fact that we're dealing all the way, when we're doing this calculation here, this ratio, it's coming from this over here. It's not coming from second differences. It's coming all the way back from our original y values. So if the y ratios are constant, it's going to be exponential. Therefore, exponential. So those are the tests that we can perform on our tables of values. Checking the first differences. If they're constant, it's going to be linear. If the first differences aren't constant, check second differences. If they're constant, it's quadratic. If not, try to do the calculation of the y ratios all the way back from the original y values. If those y ratios, which is division, are constant, then the function is going to be exponential. And last but not least, we have graphs. Now graphs, I think a lot of students find this fairly easy. How do you identify a linear function by its graph? Well, we have it right here. It's linear, and it's going to be a straight line. Because we have a straight line. Again, this one has a positive slope, could be negative. As long as that line is straight, a continuous straight line too, not something like jaggy like this that's made up of straight lines, but a continuous straight line, then that's going to be linear. So that one's linear. How do we recognize a quadratic? Well, quadratic also has a really sort of straightforward characteristic. It's going to have a parabola, which is that sort of unique U shape that you see when you're dealing with quadratics, and that will be quadratic. I think I wrote that in the opposite order, but no harm, no foul. If it has a parabola, it's going to be quadratic. And how do we identify exponential functions? So exponential functions are again a little bit different. They have a distinctive shape as well. If we look at this, and again, it's hard to tell on the graph, this is approaching but not touching 0. I should get an actual color on here. There we go. Approaching but not touching 0, and then sort of escalating really quickly and doubling, in fact, going from 1, 2, 4, 8, etc., going up. So if you see something increasing along at a sort of an increasing rate, we would call this is exponential, and specifically it's exponential growth, and that it's growing as we look at it from left to right. So exponential growth, I'll call that as increasing at increasing rate. Because again, it's not increasing at a constant rate, or I guess it's not increasing at a constant amount like it is with linear, it's increasing at an increasing rate. And same thing over here, this is just the flip side of it. This is going to be exponential as well, but this one is going to be exponential decay, and then it's getting smaller as we look at it from left to right. And same here, it's going to be decreasing as we go along at a rate as opposed to a constant amount. So that's the end of our lesson here. Again, just to recap that, what we've looked at here is characteristics of exponential functions and how you can identify them compared to other functions we've looked at like linear and quadratics by graphs, tables of values, and equations. So that's the end of the lesson. Give that homework a try, and good luck.